So we mentioned last time how we could get a notion of how likely certain events would be if we knew the distribution, and we were kind of really vague in trying to discuss how that was done. Now we want to look at our first example of an actual distribution. And it's important because it leads into a lot of notions from combinatorics that we use very commonly. So we're going to look at something called the uniform distribution. And this is a situation where the sample space is finite. So we say that the cardinality, or the size of the sample space, is equal to capital N. And each element in the sample space is equally likely to occur. So for example, we have n identical balls in some box labeled 1 through capital N. A random variable is going to be the number on the ball that we pull out. Okay, so we're going to randomly choose a ball, and we're going to assume that if all of the balls were equally likely to have been chosen, we can prove that the probability that we choose the ball labeled I is 1 over n. We can prove that from first principles. And you can show in general that for any event E, the probability that E occurs is the ratio of the number of elements in E divided by the number of total elements in the sample space. And again, you can actually prove that. Okay, so here's how we use uniform distribution. Very often we're going to be drawing objects from the sample space, and we're going to want to count the number of ways that they can be drawn. And it turns out there's two things that are important. The two main properties we have to worry about is whether or not the order in which the subjects were drawn is important. So let's take as an example a situation we have a sample space of 3 people, Abby, Bill, and Carl. And a situation where order is not as important is when we simply want to look at the number of 2 people committees that can be made. Because notice the order in which I choose those people in the committees doesn't matter. Committee's just a set. So if I choose Abby first and Bill second, that's the same committee as if I chose Bill first and Abby second. Okay. So here the number of ways I can draw 2 people committees does not depend upon the order in which the people are drawn. However, sometimes order is important. So if I look at instead the number of ways I can choose a president and a vice president, okay, I'm filling 2 different positions. So there it matters whether Abby is chosen to be president and Bill vice president or vice versa. They're not the same thing. Okay? So when we're looking at arrangements of things, or we're looking at filling positions that are not the same, order is going to be important. A second consideration that's very important when we're counting the number of ways something can occur is whether or not the sampling is done with replacement. And what that means is if we take something out of the sample space and then we put it back in, that's sampling with replacement. We replace that object after we draw it. But if we don't put the object back in, then it's sampling without replacement. And these two things, order and replacement, are the 2 main things that are going to determine how we're going to count the number of ways something can occur. Let's look at the first example. So I'm going to draw our objects from N without replacement, and order is not important. Okay? When we do that, that's called a combination. And so if we want to ask the question, what are the number of ways we can draw our objects without replacement when order is not important from N objects, it turns out that this is the following quantity: n factorial divided by r factorial times the quantity n minus r factorial. And we sometimes use this symbol to represent this quantity. This is called the binomial coefficient. Okay, it's sometimes pronounced n choose r. Another way of interpreting this is very useful, is that we can also think of n choose r as the number of subsets of our objects that can be made from n objects, right? Because when we're choosing subsets, the order doesn't matter, okay? And so both of these interpretations are very useful. Let me show you why this is very handy. Suppose, for example, we have a deck of 52 cards and I deal you a 5-card hand. How many different 5-card hands can be dealt? Well, here I'm choosing 5 from 52 without replacement, and in a card hand, order is not important. So you can go ahead and you can compute this number. You do this on your calculator generally, and you get that, so it's close to 2,600,000. So notice these clever ways of counting things, okay? We usually think of counting as being kind of a trivial thing. We all know how to do it. But this is a situation where no human being could possibly count this, okay? But yet we can do it on a calculator in 10 seconds. Now, what if we're drawing with replacement and order is important? This is what we call a permutation, okay? And we can actually derive the formula. It's not hard. Suppose, for example, we're filling up our positions. How many choices do I have for the first position? Well, I have n, right? And you notice that for each of those n choices, I have n minus 1 choices for the second position. Okay? So these are the number of ways I can fill the first 2 positions. And I keep doing this till I get finally down to n minus r plus 1. And you notice if I multiply this by n minus r factorial, I'll end up getting this quantity right here, okay, which is sometimes read as n permute r. We use this symbol sometimes. And this is a number of ways we can draw our objects from n without replacement where order is important. Okay? I'll give you a simple example of how this works. Suppose we have 4 letters, M-A-T-H, and we want to know how many different strings can be formed with these letters. Well, I'm going to choose 4 from 4 without replacement. Obviously, in forming strings, order is important. And so the answer is 4 factorial, which is 24. Okay? So notice that when we look at n factorial is the number of ways n distinct objects can be rearranged. Okay, it's a number of arrangements of n objects I can make. Now, so we've covered the 2 cases of without replacement. Let's see what happens when we do with replacement. So suppose I draw our objects from n with replacement and order is important. Notice that the number of ways I can do that is n to the r power, because I have r positions and I have n choices for each position. Why? Because every time I draw something I put it back, right? So the next draw has n possible choices. And sometimes people call this Fermi-Dirac Statistics. Okay, I'm not going to call it that, but sometimes people call it that. Because it's used to describe the statistical physics of fermions, like electrons and stuff like that. Okay, if we choose with replacement but order is not important, then we get what's called Bosy-Einstein statistics. And this is a number of ways we can draw our objects with replacement when order is not important. Okay? Another way of thinking of Bosy-Einstein statistics is a classic problem, which is how many ways can you distribute R candy bars to n children? Okay, so in that case, instead of drawing, we're actually filling bins. So if we're filling, n bins with R objects, and the order is not important, and the objects are indistinguishable, we also get this. Okay, and we can make a nice little chart. Okay, here you can see order is on the top with or without replacements on the side, and these are our different choices. And I'll give you some practice problems so that you can work on that. Okay, now next we want to consider some more useful sort of distributions like the binomial, Bernoulli, Poisson, and things like that.